All right, one of the harder things to do is converting a 2D stereo drawing to a line bond drawing. And it's not hard, but we had to kind of keep a few things in mind to make these changes, to make this conversion. So what I'm going to do here is I'm going to draw, this is the 2D projection, and I've got my line bond drawing. So let's say I put things in this 2D projection and I want to figure out what this would look like in terms of wedges and dashes. Well, the way I do this, and what makes it easy for me, is that I draw in all the axial positions first. Now I'm going to define this top right carbon as carbon 1. There are books that define it differently. I have another video on this. And I define the top carbon as number 1. And then I'm going to go around the ring. If I'm looking down at it, I'm going to look at it clockwise. So I'm going to look at it going around that way. And this will give me 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5, and 6. Now, why do I do the axials? Well, the axials will always be above or below the plane. They're the easiest for me to see. So I define in this 2D drawing, the first one always has an axial position up. So anything that is pointed up in this 2D drawing is going to have a wedge. And there are 3 carbons that have 3 upward pointing axial positions, 3 and 5. So if I had something axial here and axial here, they will appear as a wedge. Now, there are 3 other axials that point down. So the 2, 4, and 6 positions, these all point down. These will get a dash. So I know these 3 black ones are wedged, these 3 red ones, white ones, 3 red ones are dashed. Now I can define the equatorials. So the equatorials will take the opposite of the axials, because the axials, you can't have 2 wedges, you either have to wedge or dash. So if we know that these are wedged, then go ahead and draw in the axials, or the equatorials here. Oop, that pen's dead. Just going to go black. If I have an equatorial attached to an axial that's going up, it's going to get a dash. If I have an equatorial that's pointing to an axial that's pointed down, it's going to get a wedge. So let's apply it. So I'm going to create all these weird methyl groups just as examples. So I've got this 1, 2, 3, 4, 5, 6 hexamethyl cyclohexane, and I want to define them as wedged or dashed. So I want to take this 2D drawing and I want to make it back into a line bond drawing. Well, the first thing I'm going to do is I'm going to look at all the axial ones. So this axial one, pointing up and down, because it goes up, this is going to be a wedge. And because this axial points down, it's going to be a dash. I've already gotten the 1 and 4 positions. So what about all these equatorial ones? Well, what I'm going to do is I'm going to draw in the axials. So this axial goes down, up, down, up, down. The equatorials had to take the opposite of whatever the axials are. So since this axial points down, it's going to be a hydrogen. The equatorial here is going to be a wedge that points up. So this one here is going to go up because the axial here is pointed down. For this equatorial, the axial is pointed up, so the equatorial has to take the opposite. So this is going to end up being a dash when you're done. For this one, the 5th carbon, axial is up, therefore the equatorial must be down. And for this one, the axial is down, therefore the equatorial must be up. And so that's it for how you translate a 2D from a 3D. Now, I'll talk about another video about how you go the reverse way, but it's kind of the same line of reasoning.